Good morning. We were waiting for you. Okay, good morning, everyone. I think we can start. We were waiting for the Director General of the Ristoli Orthopedic Institute, Dr. Anselmo Campagna, who just joined us because he kindly agreed to give us a short welcome address before we start our online conference. Anselmo, the floor is yours.
Buongiorno a tutti, scusatemi se lo faccio in italiano, spero che mi capiate, sicuramente visto gli intervenuti non sarà un grosso problema, non sarà in grado di farlo così bene come lo fate voi, non sono particolarmente abituato in inglese. Niente, intanto grazie per l'invito, grazie a Marco di aver organizzato questa iniziativa, credo che il laboratorio di tecnologia medica sia una delle ricchezze più grandi del nostro istituto e credo che mantenere i collegamenti, i contatti con tutti i ricercatori che all'interno dell'istituto sono passati nel corso di questi 30 anni di vita del laboratorio sia una cosa veramente importante, abbia un significato grande, significa per noi sicuramente una ricchezza che porta all'istituto la possibilità di confrontarsi, di tenersi aperti su tutti gli orizzonti nel mondo e non solo guardare alle nostre realtà regionali e anche solo italiane. Ovviamente l'istituto ha avuto riconoscimenti e continua a riscuotere grandi riconoscimenti e consensi a livello internazionale. L'ultimo di Newsweek ha fatto particolarmente piacere a tutti vedersi inserire tra i primi 11 all'11° posto degli istituti ortopedici o comunque delle strutture ortopediche che a livello mondiale hanno riscontrato un consenso e un'approvazione da parte dei professionisti che sono stati intervistati. È evidentemente un risultato del lavoro che l'istituto è riuscito a fare in questi anni e soprattutto le persone che hanno lavorato all'interno dell'istituto sono riuscite a fare e continuano a fare oggi, anche mantenendo questi rapporti di collaborazione, di stimolo professionale, di ricerca multicentrica che dà la possibilità all'istituto di mantenere la sua posizione e speriamo nel futuro anche di migliorarla. Quindi non posso altro che essere soddisfatto, sono molto orgoglioso di aver avuto questa possibilità, questo incarico. Per me è un grande onore, spero di meritarmelo, spero di poter fare un buon lavoro insieme a tutti i ricercatori dell'istituto, perché questo istituto non è soltanto assistenza, è anche molto ricerca. Su questo settore lavoreremo tanto perché è necessario creare sempre più forti alleanze anche con i professionisti clinici, aprirsi a nuove reti e a nuovi progetti di collaborazione che non potranno altro che portare dell'innovazione tecnologica e professionale all'interno delle attività ortopediche che vengono sviluppate nell'istituto. Porto anche i saluti dell'assessore Donini che oggi non è potuto intervenire, mi aveva telefonato anche nel fine settimana per cercare di trasmettere a me e a voi poi un ringraziamento per il lavoro che si fa, per chi oggi non è più all'interno dell'istituto e che mantiene relazioni, ma soprattutto per chi ci lavora, facendo capire la vicinanza dell'assessorato al nostro istituto, che a me fa molto piacere perché credo che sia più che testimoniata da parole anche da fatti. Noi sappiamo quanto il nostro assessorato oggi ci aiuta e ci affianca nei progetti di rinnovamento e di crescita dell'istituto, quindi lo trasmetto a voi. Forse doveva arrivare probabilmente anche un video saluto, qualunque contributo dovesse arrivare poi lo trasmetterò al prof in modo da farvelo avere così per trasmettere direttamente con le sue parole, eventualmente anche con un video, non so cosa mi manderà o ci manderà, ve lo faremo avere. niente, per me questo era solo un momento di presentazione e di ringraziamento per l'iniziativa, spero che ce ne siano in futuro altre, speriamo di vederci anche di persona perché oggi si lavora molto a distanza, ovvio che i viaggi sono sempre complessi, ma mai come in questo periodo lo sono ancora di più, speriamo di superare insieme questa difficile emergenza di carattere mondiale, le cose stanno un po' migliorando dalle nostre parti, ma purtroppo per come sono gli equilibri, le esigenze che si incrociano, probabilmente la nostra storia con il Covid-19 non è ancora finita, sarà abbastanza lunga. Questo comunque non ci ha impedito di lavorare molto dal punto di vista assistenziale, stiamo cercando di mantenere, contrariamente al primo picco epidemico, la nostra attività programmata, molto importante, questo ha dato la possibilità di continuare anche sul fronte della ricerca, perché poi alla fine è anche una ricerca clinica dove i pazienti sono un elemento importante nell'ambito dei protocolli e non tutto si può fare solo in laboratorio. E questo è al momento un equilibrio difficile da mantenere, cercare di non avere dei picchi, scusate, dei focolai epidemici all'interno della struttura, sia sul personale, componente del personale, ma anche sui pazienti ricoverati. Per il momento ci stiamo riuscendo con ovviamente una grande attenzione quotidiana agli screening, ai controlli, ma al momento le cose vanno abbastanza bene. Quindi vi rinnovo il mio saluto, i miei ringraziamenti e vi auguro buon lavoro.
Thank you, Anselmo. This was the welcome address of Anselmo Campagna, Director General of the Ristoli Orthopedic Institute. I am Marco Viceconti, the Director of the Medical Technology Lab. Welcome everyone to this celebratory conference for the 30 years of the Laboratorio di Tecnologia Medica. Being the Director General of an hospital during the COVID epidemic is not an easy job, so thank you, Anselmo, for finding the time today to join us, even if briefly. Please stay with us as much as you can, but we will understand when you have to disconnect.
Certo.
Thank you. Okay, let's get started. If you look at the program, we tried to give some logical structure to the presentation, but we had to make some exception for those colleagues who are living very far from Italy. So we're starting with the so-called Australian session, and the first speaker is my old friend, Saulo Martelli. Yeah, it arrived now. If you go in projection.
Okay. Good morning, everybody. It's a pleasure to be here, and it's very. I want to open with a thank you to Marco and everyone else that has helped organizing this this meeting. It's very good to see you all together in the same place. Also, even if that's only virtual. But okay, so what I'm going to talk today is a work that I'm very proud of that has been completed recently by myself, Margie, Enrico, and Egan. But before getting into the science, after seeing the Marco presentation, I thought that I had to dig a little bit in the past. So 70 years have gone on my time from when I was there. So in the left you see a few images that some of you will recognize. That was LTM 15 years. The part that we had, and the other images in the very beginning was the World Congress 2006 with some sweet memory about soccer. In 17 years, you see in the right, I've gone through some distance from Italy in 3 different places. in Australia, Melbourne first, and then Flinders. And only a few months ago, I joined QUT in Queensland, where I'm slowly moving from the lower limb to the upper limb, as you see there in some of the projects that we have. Together with me, of course, you see Angela and Francesco, my son. Okay, so let's get into the science at the moment. So elastic instability, as you may know, has been something that has been much in fragility fracture of the hip for almost 20 years now, and has been thought to be responsible for the steeply exponential increase of hip fracture above 60 years of age. The observations were based on two papers that you certainly know on the Lancet, where calculation of critical stress on bones and observation of elastic instability in compressing small bone cores. So on our perspective, so there is a little bit of a contrast between the concept of bone as an optimal structure to sustain load and the idea that it fractures is due to elastic instability, which is the worst thing that an engineering system can show. So we falsified the hypothesis that elastic instability causes minimal energy fracture in entire bones. We took 4 specimens. As you see, that these are all old and pretty weak bones with an osteoporotic level from -3 to -5 merely. What we are seeing here is the experiment. So we have a compressive stage that you see on your left, and a micro-CT system at the Australian synchrotron, where we could image the entire bone under a progressive load up to fracture, and the animation shows you a volume of the bone into the images. So let's have a look at what we've got. So displacement between 4 and 5 millimeters, fracture load we have a range below 4,000, and fracture energy between 10 and 20 joule. Top left, you see the force and the displacement time history and the time frame where we did image and as we normalize the forces and the energy and by the maximal displacement, by the maximum value that we calculated, we see here displaced the normalized energy, normalized by the maximal energy, normalized force, and the stiffness. The stiffness shows a decrease, continuous decrease as the displacement increases. Energy shows a linear increase all the way up to the maximal displacement, whereas the forces shows a curvature and a flattening toward the end of the curve. Let's look into the images. We can look at here at where the post-fracture or inelastic deformation has been caused. On the left, the last load step before fracture compared to the femur before loading. On the right, the fractured femur compared to the femur before loading. And in the middle, you see some area where we are looking at in details what has been displaced and what is not. It says that there is no evident permanent inelastic deformation of bone, with except to some region very close to the fracture region. On the contrary, on the femoral head, on the fracture fragment, we do see that there is a substantial permanent deformation in the head. Looking at the strains in the entire bone, we see here the DVC calculation using cell size of 6 millimeters. We are identifying some local region on the proximal head where we have peak tension and compression level. And if we zoom into those regions, we see here with the cell size which is smaller than the 1.5 millimeters, we are seeing much higher compression, reaching in some regions 16, ranging from 8 to 16% compression. In those regions of high compression, fracture did not occur. If you're looking at what it happens in the strain at fracture location, we see that those locations are displaying high tensile and shear strain. Here we have an animation. On the left is a representative animation of the three specimens that fracture in opening mode, and on the right we have the four specimens that open fracture in shear mode. So this elastic instability occur during this whole process. In the top row, we are seeing the comparison between the unloaded and the loaded at the very first step, an intermediate load step, step 4 in the middle, and the very last load step before fracture. In none of these conditions, there is an evident elastic instability happening throughout the internal volume. If we look at the cortex, middle row, we see that elastic instability happens and start to be observable since a very initial load step in the region of high compression. So on the very right of the middle row, we are seeing two regions indicated with the yellow arrow where we have a local deformation due to instability. So does that apply to the fracture region and fracture behavior? In the last line, we see two representative cases: one for cortical opening, and the other the shear failure case. What we see on the bottom right, we see that we have bending of the cortex in the very proximity of the region, and throughout the fracture line, we do not see a significant permanent deformation across the whole fracture line. In the shear failure, similar thing happens on the cortex. So bottom right, the bending of the cortex there, and then across the fractured surface, we see a region where we have crashing of the and shear, so this lateral displacement of the trunk. So what have we learned from this work here? So what we learned is that cortical elastic instability enhanced rather than disrupt mechanical support. This was evident by the fact that there is no decrease in energy absorption capacity and force before before fracture, but instead support was provided, reaching some strain level inside the trabecular bone that exceed typical failure strains that are seen in normal small bone core testing. So energy absorption capacity is mainly provided by the trabecular bone because that's where we have seen the bigger deformation, particularly starting from the subchondral bone, where the high deformation happens right from the very early loading. So I think that these are important findings, that they put another view to the femur fracture behavior as compared to the theory of elastic instability. And so this type of behavior can be used to meet the unmet need of fracture prevention, so developing better fracture model for bone. So a big thank you to everyone. Here are a couple of figures of photo. The experiment in 2015 at the Australian Synchrotron with Egon, and on the right the campus of QT where I'm located at the moment. If someone want to well, at the moment it's very difficult with the COVID restriction, but we are opening some position, and hopefully in the 2021 it'll be a better time to traveling around the world. So if this sounds interesting to anyone, these are a few links. Okay, this is.
Can I say wow? Thank you very much, Saulo.
Yep.
We're trying to experiment here with a different way to do online conferences while maintaining some one-to-one interaction. So there won't be any question right now, but during the first coffee break, Saulo and all the other speakers will be available in separate channels for you to interact with them with chat or even by direct conference call. So without any further delay, I will introduce the next speaker, Egon Perilli. Egon, the floor is yours.
Okay, thank you. I hope you can hear me. Thanks very much, and I would just like to open with this photograph with Saulo. I think that was a few months before I left Italy in 2006. So thanks for this opportunity. Start going to the top of my presentation here. Thanks for this opportunity. I'm Egon Perilli from Flinders University in Adelaide, Australia, and I moved here into Australia in 2008. First with a group in Adelaide with Professor Mick Fazzolari, who was doing what I was doing. Later on with microcity, he was doing it with histology. And then I joined Flinders University in 2011 in Adelaide. So I start with what Marco gave in the first email when he contacted us, and he said, can you present about something that you think planted a seed in the lab? And to me, I joined the lab in 2002, and microcity, the system was just purchased by the Rizzoli Orthopedic Institute, and this was the machine I was using. Actually, this was when the lab was a little bit looking better, because where I was at the beginning was called loculo, like loculus, which is little cavity. That's what it means. It even didn't have a window at the time. Then things improved. And so it's just telling you that when this machine was purchased, I had 1 year contract at the beginning, and we started putting trabecular bone in there because that was the easiest thing to scan at the time. And as you know, people think that you just press a button and numbers come out, which is not the case, because suddenly when you show these numbers to Marco, that's what you get. It's like, do you really believe in what you're saying there? And that is something which I carry with me so far, which is never really trust the numbers that the software spits out. Always double check, is it actually corresponding to something real? And at the time the only comparison was doing it with histology. So this is an example of experiments done at the beginning, my first year there. And these are biopsies, trabecular bone biopsies embedded, and then looked at with the microscope and also with the microcity. And this was after 1 or 2 years of work, and eventually we started having images that looked similar to histology, and that was telling us we're going in the right direction. But then what about the numbers? That because software were developed that we look at 3D, and two parameters came up, which is direct trabecular thickness and structure model index. And again, you had to trust these numbers, but how do you test this? This was the big thing. And luckily at the time, I came up with an idea, and it was aided by a person who will present here. This is me thinking I need somebody helping me, and Maria Cristina Bisi, who will present also in this conference, helped me building a phantom for these measurements. And this is how this phantom then worked at the time. So this is very important because measurements that you obtain with microCT by going, as also later on will be talked about by Gianluca Tozzi, at the beginning you really couldn't trust what was coming out. Only by validating your measurements you actually can start looking at correlations and then actually also getting some accurate measurements. And this is how the phantom looked like with grids in between 100 and 200 microns. And then another thing that was seated there was actually the work that just was presented by Salvo. This was the experiment done with Fabio Barufaldi at LTM, where with a group of physicists of University of Bologna, we went to the synchrotron Elettra, and we scanned the proximal femur at 22 microns, which is still so far actually the highest spatial resolution one you can find in the literature for a proximal human femur, even higher to the one that we used with Salvo at the time, a few weeks ago. So this is a few years ago. This is the images that you can see obtained back then. It is 15 years old, I think, and it still rocks. So this is something that should have happened last week, which is the launch of the large value microCT system. Because of COVID outbreak, we had to suddenly 3 months in the making of the launch, you had to give up because COVID restrictions. And this will be a media launch in the coming weeks. So watch that space, because what we can do at the synchrotron now, we can do actually with the system here. So look at that. So going back to the title that I was given by Marco to talk about. Combining bone and joint microCT imaging with gait analysis. So I can't talk about this without acknowledging my PhD student, previous PhD student Brian Roberts, and current candidate Sofia Ratania, who have done the actual work here. Abnormal joint loading and joint malalignment have previously been linked to altered medial to lateral distribution of loads, and most studies looked at bone microarchitecture and the influence of joint alignment, for example, but in osteoarthritis. But unfortunately, most of them either were compartmental, either they were looking at knee alignment and then suggesting how this could influence the bone distribution, but only looking at bone mass with DEXA, for example, or cores were taken from the knee and scanned at high resolution, and then some speculation was done about maybe what we see there is the result of loading due to joint malalignment or the way the person walks. But nobody really has taken the two things and combined and looked at the same patient with gait analysis and looking then at the bone, and in particular bone microarchitecture. So joint malalignment can cause, for example, in the case of a varus, malalignment, a higher distribution of load medially compared to laterally, and that would reflect then a higher medial to lateral joint loading, which results also in a higher knee adduction moment, which is an index for that. And this would possibly be reflected in higher bone distribution medially to laterally. And this was the study carried out together with the group at Uni Adelaide, with Dominic Kulis, that was part of this too, and he still is, and Brian Roberts, which we co-supervised, and we scanned and he developed a protocol for scanning entire human tibia with microCT, and without coring them. So this is virtual coring, where with 17 micrometer resolution, we are able to look at the pores in the cortex of the tibia, so the subchondral cortical bone, so the layer just below the cartilage. You see pores, regions. These are regions of 5 millimeter thickness, and in yellow we highlight the cortex, and in white the subchondral trabecular bone underneath. Brian did a mapping, which means systematic mapping of this, looking at the bone volume fraction in the top row, showing in red higher bone volume fraction medially compared to laterally. we have also correspondingly higher plate thickness, so the cortex is thicker, and the porosity is actually going with inverse to what I just said. And this is for virus aligned. In non-virus aligned, instead, we have the opposite. So that was good, but the problem is how do they work? So we combined this with gait analysis, and what was found is that the near action moment correlates positively with the medial to lateral bone volume fraction, and the external rotation moment, the peak external rotation moment, with the medial to lateral bone volume fraction ratio. So there is something there related to gait and to joint alignment, which we can look into. And so that was the bone. What now? That's always the question I got at the conferences. Okay, you look at the bone, you look at the gait, and what's next? And it's not just bone. There is also cartilage there. And this is then the next step. And cartilage morphology can also be affected at the same time. And it's the story of the chicken or egg, what comes first. But we don't know. Right now, cartilage studies have mainly looked at, so this, I'm just showing here the knee adduction moment, which is higher, which corresponds in the literature to regions, for example, showing or suggesting thinner cartilage. But nobody really has taken these specimens and looked at high-resolution imaging, with high-resolution imaging at the cartilage and gait analysis on the same. Moreover, nobody really has combined bone, cartilage, and gait. Some studies have used MRI, but MRI, magnetic resonance imaging, has a spatial resolution of about 1 millimeter, and that's about the thickness of the cartilage. So the slice thickness corresponds to the thickness of the cartilage that we are measuring. So regions with thinner cartilage might not be captured. And so I'm showing here the current study by Sophie, where we are looking at the cartilage thickness of excised tibial plateaus using micro-CT in end-stage knee osteoarthritis undergoing total knee replacement, and the relationship with the preoperative knee joint loading indices and joint alignment. So this is the age, about 70 years old, BMI about 32, and they were, on average, they were virus aligned, but slightly virus aligned, but we had a mixed group there. So gait analysis was done prior to surgery, and the reason why we thought we can see cartilage is because when we developed a scanning protocol for Bryant, we saw that there was actually the cartilage above. By trying to maximize the signal-to-noise ratio for seeing the pores in the cortex, we actually are visualizing most of the cartilage. That gave us an indication that we can actually see it. And by thresholding it properly, you can actually look at the cartilage here in blue. And this is a mapping of the thickness performed on excised tibial plateau on a virus aligned, and you can see the area of the nuded cartilage on the top left, which is anterior medially. Now, we looked at the cartilage in those regions that previously were identified by Brian in his paper as being those that were more relevant for looking at differences in the bone. So we were just looking at the cartilage above in the same regions, in the same patients. And then we looked for relationships between the cartilage thickness, joint loading indices, and mechanical axis deviation. And what we see here is that there is a significant relationship, a positive correlation anterior medially with the knee adduction moment, and a negative with the cartilage thickness posterior laterally, for example. Now, if we look at the external rotation moment, we find a significant correlation, positive, with the cartilage thickness anterior medially, and if we look at the medial to lateral ratio, this is even a stronger correlation. If we separate the tibial plateau into cartilage, subchondral trabecular bone, in between we have the subchondral cortical bone, which is what we saw before. Now we can look at all these three things at once. And what we found is that these relationships that we found with the medial to lateral cartilage ratio and the external rotation moment is opposite to what we found in the bone. So regions with thicker There must be something there which drives the joint as a whole, which decreases the cartilage and increases the bone underneath. How does this compare to normals? That's another question that we got because we were just looking at osteoarthritic patient. So we have looked at tibial cartilage, subcondylar bone plate, and trabecular bone microarchitecture in varus and valgus osteoarthritis patient versus so-called controls, non-OA. And this is pictures, photographs on the top, micro-CT image with the cartilage distribution in the middle, and then the bone underneath, the subcondylar trabecular bone. And you see that, in the controls on the left, in blue, there's a 1 millimeter thick cartilage all over the medial and lateral plateau, whereas in varus aligned, we have less thick cartilage by darker blue and brighter colors laterally, which means thicker cartilage, and the opposite is seen in valgus. And if you look at the bone underneath, we can see that compared to controls, where we have thinner cartilage, we actually have thicker bone, and the opposite in valgus. This is a different view, a coronal view of the same specimens, where you can appreciate as a cut at the green line, cartilage enormous in the first row, which is almost gone until medially, the blue part in the second row, and you see very thick medially actually in the valgus lines. And these are now the ratios, just showing the statistical significances between the groups that you can actually find in the paper. Now, how do we translate this into clinics? And this is a question, very fresh paper with Dom that you see here. What about, how can we look at this in a patient without taking, we can't do micro-CT imaging, we have to take the tibial plateau from the patient. So the only thing you can do is doing at the moment, for example, PQCT or HRPQCT. So we have a PQCT here in Adelaide, and with Dominic, we co-supervised an honor student, and we investigated in vivo new volumetric bone mineral density and working gait mechanics in healthy people. So this is on a patient with the density calibration phantom here that you see on the right, where this is a subject, a volunteer actually, where we looked at the bone distribution on 19 volunteers, healthy young volunteers, and we find that anteromedially, posteriormedially, posterolaterally, we have a sort of uniform distribution of bone, but anterolaterally slower. That is similar to what we found in OA, but the difference is that posterolaterally we have more bone in normal. So something is telling us that something might be shifting with the pathology. And also here, the medial to lateral ratios are similar, but in part different to what we have in controls. And how does this go in OA? How does this go with the gait analysis? Well, that's interesting. We found actually not many relationships there in the normals. So it seems that the pathology exacerbates relationships that might be there or hidden. And the only thing that we found is actually a positive relationship between external rotation moment and the medial to lateral bone mineral density ratio, which is opposite to what we found in OA. So there must be something there which, with the pathology, shifts these ratios, the way they walk, might influence it towards the bone mineral density shifting from one compartment of the knee to the other. It might be joint alignment, but also what we have here, the knee adduction moment and the external rotation moment play a big role. And this is a non-invasive way to look at it. We are not there yet with the cartilage, but it's a first step. Thank you very much.
Again, wow. I don't think we could have started better than with these two presentations. Amazing work, Egon. Thank you very much. So both Saul and Egon will be so kind to stay with us until the first break and to answer your question. But we now carry on. And I give the chairing to Fabio.
Here I am. Good morning to everyone. I'm Fabio Barufaldi, one of the senior researchers of the Medical Technology Lab of the Rizzoli Orthopedic Institute. And now I'm going to introduce one of the founders of the laboratory and now director of the Medical Technology Lab, Professor Marco Viceconti. Well, when I first met Marco in 1991, the lab was at the very first stage, and just to give you an idea of those old days, the World Wide Web had yet to come. And since that time, me and Marco have spent our professional lives as colleagues in the same office for 20 years, sharing also important and personal, professional and personal events. And it is therefore a real pleasure to give the stage to Marco, because I'm sure that it will take us in an exciting journey to in the last 30 years of biomedical engineering in orthopedics. Okay, it's your time, Marco. Go on.
Thank you very much. Can you see my slides?
Okay.
Good. So, believe it or not, I am quite emotional. This is a big thing, guys. But anyway, I'll try to do my best. When I was trying to prepare this presentation, I faced two problems. The first is how to summarize 30 years in 30 minutes. But the other was that as I was trying to tell the story of the lab, I keep falling in my own personal story. And the reason is that in my head, I struggled to separate my own professional career and the development of the lab. So in the end, I decided to give it up. And what I'm offering you is my own personal view of the history of the Laboratorio di Tecnologia Medica. So let's start from my own history. I was a student in mechanical engineering, and I had two influential professors, Alessandro Freddi and Gabriele Molari. Alessandro taught experimental mechanics, and Molari taught computer-aided engineering. But because I was a computer nerd, this is my first computer, believe it or not, I decided to do my thesis with Professor Molari, which at that time was working with people like Glauco Mazzotti to the development of one of the first solid modeler in the world, Aliseo. So I had fantastic opportunity of learning in that period. I ended up working on shape optimization, and I started to do in a very confused way what today would be called bio-inspired computer-aided optimization, looking at tree remodeling and things like that. One of the papers that really impressed me, although I think I understood probably 10% of it at that time, was this paper from Dennis Carter and David Fiery about bone remodeling. This idea that our skeleton would adapt to changes in the biomechanical environment somehow impressed my mechanical engineer head. But yeah, this was just an intellectual exercise until in 1989, this is me at that time, I moved from the University of Bologna to the University of Florida to work with Professor Ali Sirek. And at that time, there was not much communication. So when I got there, I really have no idea what I was supposed to do with Professor Sirek. And he said, look, I don't care about what you're doing in Bologna. I think you should do biomechanics. At the beginning, I was terrified because my knowledge of biology was pretty much zero. But eventually, I accepted the challenge. I started to work. And when I left the United States, I had submitted what would become my first publication, a paper on a damage-based theory for bone remodeling that was published in 1990. That somehow set the fate of my further career because I was so in love with biomechanics that I decided that was what I wanted to do in my life. And then there is a lot of luck in my personal history. Another lucky passage was that by some very random events, I ended up talking with Armando Giunti, and he offered me a job to start up a lab. At that time, it was tentatively called Materials Technology Lab in the newly established Codivilla Putti Research Center. Rizzoli was a well-known orthopedic hospital, but he was making this transition to a research hospital. At that time, we only had these two pictures. These are Polaroids, and the older of you might remember this instantaneous development films. But what they show are empty space. And that's, in fact, what I got. I got 600 square meter of empty labs, about 1 billion lira, which would be roughly something in the order of €1 million, to buy instrumentation. And notice, I had less than 2 years of a research experience at that time. I had absolutely no clue what to do. And in fact, our first decent paper came out 5 years after. And this 5 years were really years where we try to understand what could be done in the most general sense possible. I had this money to spend. I went to talk to Professor Freddy. He listened to me and he said, well, you probably need an hydraulic testing machine. So we bought an Instron, an 8501, which is still working amazingly after 30 years. And then I wanted to buy computers, of course, and at that time, the absolute best in computer-aided engineering was Intergraph. So we bought 2 Intergraph workstations. The official price of this workstation at that time was $500,000, hardware and software. We paid much less than this, but still we paid a fortune, and after only a few years, we trashed them because they become brutally obsolete. But that's the way it is. Giunti gave the leadership of the lab to a younger surgeon, Aldo Toni, who had just designed a new anatomical cementless hip replacement called ANCA. And so the idea was maybe we could look into this. But honestly, we were very confused about what we could do. And this is the proof of our early attempt. This is an historical picture, 1990. We are in Riga, in Latvia. You can see myself, Aldo Toni, Arturo Natali, director of the medical faculty of Riga, John Middleton, that probably many of you remember, and Ivar Knetz, who was director of the Technical University of Riga at that time. Ivar died a few years ago. Aldo managed to insert us in this EU-funded project, which was about ceramic. Honestly, we had no clue what we were supposed to do there. But for me, it was a huge opportunity to start to internationalize, to meet people from other countries, etc. Fabio joined me, and we were given a pretty dirty job. They said, well, look, we are checking bone remodeling and comparing X-ray of the same patient. You should make this quantitative. But, you know, everything available at that time was 8 bits, and analogic X-rays had about 12, 14 bits of gray level. So we developed a homemade way to do the dynamic range expansion, which was published in '92. Really, a key person in this work was Maurizio Abate, who was a hardware provider who gave us a lot of help in this work. And I got in touch again with Maurizio after many, many years, 2 weeks ago. So serendipity again in action. Interestingly, when we finally had a working system, we demonstrated that that information was not in the X-ray, in the sense that the variability due to the chemical development of the film would be larger than what we were supposed to measure. So essentially, we couldn't make a quantitative measurement. So overall, it was a failure. Also, of course, we learned a lot in the process. Same was for this thing. Aldo Toni had this idea, which was a great idea. Take an Elizarov external fixator, add some robotic control to it, and use it to do automatic extension and realignment of bone segment in fracture fixation. So in order to avoid the high radiation dose on the hands of the orthopedic surgeon who has to perform this maneuver manually under the BIVU, under the continuous X-ray system. It was a great idea, but we had no clue about robotics. I mean, I never studied robotics, and so we did something. It kind of worked, but obviously this was not our job. So my level of confusion was very, very high at that time. And then finally I had a breakthrough. I went to my first conference, my first serious conference, the 8th Congress of the European Society of Biomechanics, which was organized in '92 by Aurelio Capozzo in Rome. And there I met for the first time some of the key people of biomechanics in Europe in that time: Rick Iskey, John O'Connor, Peter Walker, Aurelio himself, who remain a friend for all our career. For me, this was a key moment because I realized that really what I could do, that the topic where I did have some decent skill was biomechanics, and that's what we had to focus on. Luca Cristofolini the other day told me a story. At that time, he was a student, but he was already curious about biomechanics. So he wrote to Aurelio Capozzo and he said, well, I'm a student. I heard there is a conference. And Aurelio invited him to attend the conference for free. And he even gave him accommodation at the Olympic Village where the event was organized, again for free. So Luca was an auditor at this conference as a young student. And this was the style of our friend Aurelio Capozzo. Okay, but the real big event for me, the breakthrough in terms of networking, is another conference the year after, the International Society of Biomechanics, 1993. I'm pretty sure a few of you remember that conference. It was an amazing conference, both from a scientific point of view, but also from a social point of view. We had our banquet on the Bateau Mouche, going on the river across Paris, amazing. And there I met and started my friendship with people who remain key reference for me across my career. I put some name here. I'm sure you recognize many of them. I also put Roberto Fogliardi, who is not a biomechanician, but again to show the serendipity and the networking. Roberto at that time was a student in bioengineering. At the conference, we met each other, we became friends, and then he decided to take a completely different career. He went working for a company called Aetra, and Fabio Barufaldi and I worked with him a few years after when we were working in the telemedicine sector. So again, it's a small world. And finally, we started to work on biomechanics. Luca Cristofolini joined first as a master student thesis, then he started his PhD, and in '95 he published the first biomechanics paper of our lab. At that time, it was a beautiful work looking at the effect of each muscle on the deformation of the femur. In reality, we were preparing to our success, even if, this first year are pretty opaque in terms of publications, results, and what's not. But so I tried to think what made this very humble beginnings into a success story. And I think that there are four things: luck, hard work, stubbornness, and then there is something that in Italian is ignorantezza, and if you don't know what it is, look at Paolo Cevoli video on ignorantezza. I tried to translate it in English with ignorantness. It means that in spite of the fact you don't know, you jump behind the barrier and you do things that you're probably not ready for, but with a lot of enthusiasm and a lot of energy, somehow you compensate your shortcoming, and by trial and error, eventually you succeed. I think we had a lot of that. We were very arrogant. We were very, not arrogant, how can I say? We were ignorantness. It's a definition. And in fact, 1996 is the year where we opened the wings. The labs become international. That year we have two overseas visitors, Tim Harrigan from the United States and Brian McNamara, that will work with us for 2 years. And we published a number of papers that year, and each of those papers is somehow the seed of something. So with Tim Harrigan, I published a paper on bone remodeling, somehow the continuation of my initial work with Professor Sirek. We published a paper on the effect of autoclaving on banked bovine bone. At that time, we had the mad cow disease, and this was the first time where a clinician came to us with a practical problem and we did the research and helped them to solve that practical problem. And this then became a pattern for our lab. We are a very translational lab that works very close to the clinical practice. We published the first paper on describing, for the first time in the literature, the fretting wear and fretting corrosion mechanism in modular neck hyperostasis. We've published a first paper on the design of a hip joint simulator, and then soon after Roberto Cianci joined us, and then Saverio came in, and the whole tribology department in our lab started. Luca, what is still today probably one of the most cited papers of our group, where he did a systematic comparison between composite material bone analogous and actual cadaver bones. And then Massimiliano Casali and I published the standardized femur program. Again, this was a seed. In itself, it was not much. We simply made available publicly a CAD model of these bone analogs so that people could easily model without wasting time. But it was the beginning of a computational activity. This was started with a collaboration between our lab and the Cineca Institute, the Supercomputing Center in Bologna. This is a collaboration that has been running since then. What we were doing at that time was very rudimental. You can even see in the pictures and the resolution of the medical imaging. Again, it put the seed on many, many things that came after. One important thing was that on this project, I hired a guy from San Marino called Massimiliano Casali, and Cineca hired a young mathematician, Barbara Massari, and they worked together, and they fell in love, and they got married, and this is the result. This is Giulia Casali, the beautiful girl on the left with the leg on the word. She is a little champion of rhythmic gymnastics in San Marino. Why I'm showing you this? Because already in those years, another thing emerged. The lab was not only a place to do science, it was also a place where a lot of young people lived some fundamental years of their life, where they established their sentimental relationship, their social networks, they defined themselves professionally, and this has been an amazing journey, which I'm still enjoying today with my latest co-workers, and this is a beautiful thing. The period between 95 and 2000 is really the period of consolidation. In many regards, the assets, the organizational asset that we adopt is still reflected in the lab today. Max Baldaiani joined us, and he picked up my work on modular necks and started to work on biomechanics of material. Saverio pushed through and develops the tribology activity. Fabio specialized in medical imaging and health technology, and Luca continues his work in experimental biomechanics. And I finally go back to my first love, and I start to develop the computational biomechanic aspects of the lab. I put the photo of these four people here, not because they are the most important, but because they are the first. Those are my co-workers that broke the ice with me and started to do computational biomechanics. Cinzia, Marek, Roberto, Deborah. There is one missing, Luisella Bellingeri. I couldn't find a picture of her online, unfortunately, but I want to mention her as well. Again, the quality of work that was done at that time was pretty rudimental, I have to say, but we learned a lot by our mistakes, and that was fundamental to improve over the years. In '99, I went to spend a short sabbatical at the University of Oxford, and this is important for two reasons. The first, that I did some beautiful work with Christina Polgar in the area of computational biomechanics, but more important, I had the opportunity to work under the supervision of John O'Connor, and in this environment, in this very conductive environment, the idea of patient-specific modeling started to form in my head. While we were doing this, the scientific productivity of the lab and the size of the lab, of course, grow almost linearly. This is the number of papers we published from 1993 to 2011, and as you can see, there's been a constant growth. The opportunity to develop this idea of patient-specific modeling came when Marco Manfrini, an orthopedic surgeon focused on pediatric oncology, came up with us with an interesting problem. How to decide if there was a risk of refractoring in the rehabilitation of children who had massive reconstruction due to tumor resection. Fulvia today just joined our group, and she picked up this project. This became her main project for a long while. And with Fulvia, we planted some of the most important seeds in the computational side of the lab, developing patient-specific finite element model from CT scans, developing patient-specific multibody dynamics models from gait analysis and MRI, and so on. This is another topical moment for me. In 2002, I went in Calgary at the World Congress of Biomechanics, and I heard a plenary lecture from this New Zealander, Peter Hunter. And Peter was giving the words to my thoughts. He was saying, yes, Marco, this idea you have of patient-specific modeling is not something that's valid only in orthopedics. It is global. We can do so much more. We can do multi-scale from the molecular to the whole body. The sky is the limit. And for me, this was like St. Paul on the road to Damascus. It opened a whole new view of what we could do with our modeling techniques. This became my obsession. And following here, there was this journey that started in 2005 with the publication of the white paper where we introduced the concept of virtual physiological human in Europe, and then with a number of other events that eventually positioned Bologna and the Medical Technology Lab as one of the key players in the VPH initiative. This is another interesting element. This is the number of invited talks that we received in those years. And as you can see, we started from pretty much nothing until 2002. And then we arrived to have 13 invited talks in 1 year, which suggests that there is the prestige of our lab was growing conversely. The last decade before this one was really the period of excellence. I listed here in random order. I'm not saying they are the most important achievement, but we developed one of the best CT-based preoperative planning for hip surgery, HIPOP. Egon already explained the seminal work that he and Fabio did on the micro-CT histomorphometry. This group and Massimiliano work on the micromechanics of Cancello's bone. We see that the idea of statistical finite element model, and with it the idea of in silico trials before anyone was even knowing the term. We developed some very crazy designs for joint replacement, like the CLU stem, which was not very successful commercially, but as far as I know, there is still the best performing joint replacement ever. Massimiliano did a beautiful piece of work with Cecilia, who is presenting later today, on the effect of antibiotics on PMMA, and so on and so forth. Yeah, the infamous Mitch redesign that many of you were involved in. All this work is documented in the many publications of our lab. In 2008, we won one of the largest European funding available in the VPH area, and the VPHOP project started. It was a grand science endeavor. It involved 20 organization, opportunity of my life. I was the coordinator, and almost everyone in the lab was involved. But those were also the year where the diaspora began. The lab had become too big for the physical spaces, too big for the vision of the institute, too diversified for our narrow mandate of focusing only in orthopedic diseases. The first piece that detached from us was the software development team. And in 2006, Deborah Testi and Alessandro Chiarini left the lab and went to establish the Biocompetence Competence Center, which for 6 years developed software for biomedical research at the highest possible level. And then this became a trend. And I'm sorry if I forgot you. I put some picture of some of you here. I'm sure there are many other, but these are all people that started somehow in the lab for a little or for a longer while, and then they moved their career abroad in other country, and they're doing beautiful work. And we already see 2 examples of Saulo and Egon this morning, and many other we'll see today. But it was a sign that we were bigger than the container. We were overflowing, okay? And this was the primary reason why in 2011, I accepted the invitation of the University of Sheffield, and I left the lab and I went to UK to establish the Insignio Institute for In Silico Medicine. I had this desire to demonstrate that in silico medicine required grand science, large institute with a lot of collaborators, a lot of academics with different expertise. And the history showed that I was right. I mean, after 7 years when I left Sheffield, these were the figures of the Insignio Institute, and it's been and still is a very successful initiative. Now, back to Bologna, 2018, later 2018, I rejoined the University of Bologna and the Ristoli Institute, and now there is the present. And the present is shining. This is a picture that represents the vision of the lab today. We can cover all the bases of the entire life cycle of health technologies for neuromusculoskeletal diseases. And I give you 2 numbers. In 2019, we published 35 papers, and this was the largest number ever. So last year was the best performing year in the 30 years of history of the lab. And we attracted over 3 million of new funding in the last year or 2 years or so. So these are good figures that show that the lab is very healthy and is growing again at an important pace. I'm not going into the detail, but there is a million of things going on, very exciting. We're talking about patient-reported outcomes in the RIPO registry. We're talking about new schools of in silico trials. The MIMAS project is looking at the MRI safety of joint replacements, and so on and so forth. We just got a huge grant from the European Commission, 8 million, in a project called In Silico World that starts in January. So a lot of future ahead. And in fact, I would like to close with a famous sentence from Winston Churchill. Now, this is not the end. This is not even the beginning of the end. But it is, and I'm pretty sure of it, the end of the beginning. I thank you very much.
Okay, thank you very much, Marco, for this, well, how can I say, emotional mix-up of personal and professional stories. Thank you again. I remind to the audience that we did not schedule time for the questions about after the presentation, but you can use the specific tables and the breaks to pose questions to the speakers. Well, therefore, I guess we can move on with the next session, that is experimental biomechanics, chaired by Fulvia Taddei. Thank you.
Okay. Can you hear me?
Yes, we can.
Hi, everybody. I'm emotional to be here. Hi. Okay, so we can start the experimental biomechanics session. So the first speaker is Massimiliano Baleani. And let me try to understand if I had to do something or if he's going to connect by himself or not, because it's not still clear to me. Am I supposed to do something to help Massimiliano Baleani?
Can you hear me?
Yes, we can hear you, we can see you, and no, Fulvia, you don't need to do anything.
Okay, great. So,
Massimiliano, you should be able to share your screen.
Can you see the screen now?
No.
Not yet.
Not yet. Perché non fa?
Why I'm not surprised.
No.
In the top top right, there is the camera, the microphone, and a square with an up arrow. The square with the up arrow is the sharing of the screen. And then you select desktop.
Okay.
Something is happening. Yeah, we can see your screen now. Thank you.
Okay. Okay, let's start. Okay, let's get started. Joint prostheses are used to replace a dysfunctional joint of the musculoskeletal system. From a biomechanical point of view, joint prostheses must restore, as near as possible, the natural joint kinematics, withstand physiological loads as applied to the joint during daily activities, ensure the appropriate transfer of load to the host bones, and, of course, ensure biocompatibility when used in vivo. Manufacturer must demonstrate that joint prostheses meet the mentioned biomechanical requirements. How can this be achieved? Well, this can be achieved by carrying out preclinical validation. Preclinical testing is carried out in accordance with the relevant international standards, such as those published by the International Organization for Standardization and American Society for Testing and Materials. Experimental testing is performed to investigate the wear behavior or the mechanical properties of a joint prosthesis. The rest of my presentation will not focus any further on wear behavior, as that falls within the scope of the next talk. Okay, mechanical testing of joint prosthesis is part of the regulatory analysis process. Testing of joint prosthesis is performed according to technical standards when those are available. Some of these standards identify in essence the worst-case loading scenario, and they basically set all the test parameters such as loading level and test duration. Two examples of such kind of standardized procedures are shown in this slide. It must be mentioned that regulatory authorities normally expect adherence to active technical standards. In absence of standardized procedures, the option is to develop internal procedures. In such cases, the rationale followed to identify the worst-case loading scenario must actually be supported by existing clinical data. Here is an example of this approach followed to develop a procedure for testing unicompartmental knee prosthesis. The mode of failure of unicompartmental knee prosthesis were investigated by reviewing the literature. The review focused primarily on the causes of mechanical failure as they occur in vivo. Then, an experimental model was developed so as to replicate the worst loading scenario, with the loading level itself being derived from the standard method for testing a tibial tray. Okay, so let's assume that we have a protocol available which can be used to carry out an experimental test. Now, it's not actually feasible to test every device in every configuration which may be available through inventory. However, we can perform a study which uses the finite element analysis to identify the worst case configuration within the variety of combination available. Now, finite element analysis can be used to predict the stresses within the implant. This analysis is a powerful tool to identify any region where high stresses are induced and, if necessary, can be used to optimize the shape of, for example, a monoblock stem. This approach improves the efficiency of experimental tests because the threshold performance requirement is generally met on the first try. Well, What will happen if the test is unsuccessful? The integrated approach, as I mentioned in the previous slide, is still effective. In general, the problem lies in the mechanical performance of the metal alloy, specifically in the established fatigue limit. Indeed, the fatigue limit of a metal alloy is sensitive to the microstructure of the alloy and the presence of surface features, which might raise the stress induced. This means, therefore, that any new surface treatment, any new surface coating, as well any change in the manufacturing process may have an effect on the fatigue limit of the alloy itself. Now, these changes, even if they are small, may have a significant impact on the performance of the designs which work at high stresses. Therefore, new solutions are welcome. In essence, what we need to do is do our homework and determine the effect that the new solution might have on the mechanical performance of the alloy. Okay, all that's all once is good so far. I have described the effectiveness of the integrated numerical experimental approach for predicting of mechanical performance of monoblock devices. However, joint prostheses include modular designs. Now, modular designs became popular in the 90s. On this slide, you can see an example of a modular total hip prosthesis. Now, there are potential benefits to having a modular implant, and this includes, for example, the use of different materials whose properties are actually adapted for the working condition of each single component, a greater intraoperative flexibility, which will allow operators to adjust the implant configuration to the patient anatomy. Also, a easier revision surgery, because the step to retrieve the implant components can be limited only to the part which has been damaged. And finally, basically for decreased inventory. However, on the other hand, you also have concern with which now become an issue, for example, junction stability, the mechanical strength of the junction itself, generation of ions and debris, which can be responsible for adverse tissue reaction. These have been cited continuously in the literature since the introduction of modular designs. Now, over time, standards concerning issues around corrosion of metallic implants have been introduced and became available. The first one listed, the ASTM F1875, contains a recommendation for fatigue corrosion testing of head-neck junction. Despite the standard, there is clinical evidence that junction of modular designs are a source of debris themselves and that they may increase the risk of adverse tissue reaction. Of course, standards continue to evolve, and an effort is expected that new knowledge which we have acquired will actually lead to the draft of the new development of new standard. In the meantime, we have no choice but to carry on with designing of specific preclinical testing to investigate the damage which occur on the junction interfaces. Now, there are a couple of examples which I'll give you. Some prostheses include a modular acetabular cap consisting of two components, a polyethylene liner and a metal shell. In general, a locking mechanism provides a secure fit and also stability for the polyethylene liner, and also it should minimize the risk of backside damage, also called backside wear. However, micromotion occurs at the shell liner interface due to physiological loads. The amplitude of micromotion is related to the locking mechanism, the stiffness of the cap, and the inner feature of the metal shell. Experimental tests can be designed to investigate the backside damage in modular acetabular caps. The experimental models should replicate the worst-case scenario. This experimental approach is effective in comparing different prototypes, but increases the costs and time that it takes for the preclinical validation of new implants. The current development in finite element analysis, however, might actually allow reliable prediction of the backside damage and guide the development of a new implant, decreasing costs and time that it takes to get this in the market. Okay, now, the second example is that of hip prosthesis, which include the modular neck. The neck stem junction is a potential site for mechanical failure, and it can be a source of iron and metal debris. Indeed, this junction is susceptible to fretting corrosion, also referred to as mechanical assisted corrosion. An experimental procedure for testing modular neck design was published in the 90s. Since then, an extensive body of research has accumulated. In essence, what we have learned is that preclinical validation of this design must include, but not be limited to, the estimation of mechanical performance, that the relative micromotion at the junction interface must be measured because micromotion amplitude plays a role, no, an important role in fretting corrosion damage process. The amount of metal debris and iron released must be evaluated since the release of damaged products can trigger adverse local tissue reaction. Now, since the prosthesis design, the material, the manufacturing tolerances, and the surface treatment play a critical role in limiting the damage caused by fretting corrosion, the preclinical validation of this design is time and cost consuming. So, the question is, can finite element analysis help in assessing the performance of modular neck designs? Yes, it can. It can be used to investigate the relationship between implant design factors and the contact condition at the junction interface. Now, different solutions could be evaluated before experimental tests in the avoidance of having to try and retry different prototypes. In essence, we can reduce the event of trial error. The main limitation of finite element analysis is that, so far, they cannot be used to predict the damage phenomena which may occur in the neck stem junction. Okay, last but not least, joint prosthesis must ensure proper load transfer to the host bones. Okay, we have two different types of implant fixation, cemented and cementless fixation. Cemented implants achieve stability from a bone cement mantle once the bone cement is cured. An integrated numerical experimental approach is effective in reducing stress in the cement through the optimization of the implant design. However, we know that bone cement mechanical properties may cause long-term problems. Indeed, many studies have attempted to enhance the long-term performance of the bone cement mantle, but I will not dwell with this subject any further. On the other hand, cementless fixation relies primarily on press-fit stability with long-term stability occurring through the secondary subsequent ingrowth of bone. Okay, we know that excessive early micromotion might prevent bone ingrowth and excessive strain may damage bone tissue. We can perform experimental studies to determine the probability of joint prosthesis. However, we must consider that many factors such as implant design, quality of host bone, loading condition, implant alignment may affect the primary stability, and it is not possible to explore all these conditions experimentally. Now, in evaluating the primary stability of any new implant, the integrated numerical experimental approach is actually useful. The experimental study can explore a subset of possible combinations which may occur in vivo. Then the collected data can be used to validate a numerical model. Finally, the numerical study can be used to investigate the changes in primary stability due to the variability in the properties of the bone itself, or the bone anatomy, or the alignment of the implant. Now, this integrated approach can be used to evaluate the implant prototype under a wide range of conditions, which are more representative of the variability which is experienced in clinical practice. Okay. In summary, we can say that mechanical testing of orthopedic implants is an important part of the preclinical validation, but a purely experimental approach is time and cost consuming. That an integrated numerical experimental approach has the potential to make preclinical validation much more effective, and that the challenge is to improve the prediction accuracy of finite element analysis in all cases where interfaces play a main role in the implant performance. And that's it. Thank you very much for your attention.
Thank you. Thank you, Mark. The next speaker of this session is Saverio Affatato, that will talk about tribology of joint replacement. Please, Saverio.
Dice?
Yeah, we can see your screen. You can start.
Okay.
Oh, God.
Thank you, Fulvia. Hello, everyone. I am Saverio Affatato, and when I started in the lab, I was very young. My activity initially focused on the elixir of sector, a short period. So then I moved my interest towards tribology. What is the tribology? Tribology is the science of the rubbing that derived from the Greek term. The word tribology was used at the first time by Jost in 1966. And the ordinary equivalent English language report that tribology is the science of friction, lubrication, and wear. Our interest in this talk is on the wear. What is wear? Wear is the progressive material loss when two surfaces slide between them. Wear is a complex phenomenon. And the first attempt of about the wear is back before Christ. Lucrezio observed that the phenomenon of the ring on the finger and the rubbing on the foot on the statues. More recently, Leonardo da Vinci approaches this problem, solving some questions, some problems due to the friction and the wear. Tribology is not just related to the mechanics device. Human joint, lubricated by the synovial fluid, work for a lifetime, but accident or other complication can modify the anatomy, producing pain, problems with the walking, etc. So, to solve this problem, and alleviated pain and restore the articulation, the bed joint is replaced with a prosthesis. In this case, it's a hip prosthesis. A hip prosthesis restores have the aims to restore the pain relief and the restoring of the joint function. A view of an intervention of an hip prosthesis, we can view the skin and the muscle are cut, the head of the femur resected, is inserted a stem the modular neck, the stem, the modular neck, the head, the accelerator cup, and voila, le sont faites. Today, with a new anterior approach, the muscle of the patients are preserved, and the patient can move to walk the day after. The biomaterials used in for a knee prosthesis are various: metal alloy, ceramic alumina and zirconia, alumina toughness zirconia, polyethylene, ultralight molecular weight polyethylene, and the bearing are usually metal on ceramic, metal on polyethylene, ceramic on polyethylene, ceramic on ceramic, and metal on metal. And this is a view of typical biomaterials used for a hip prosthesis. But, however, although the material is perfect, the prosthesis could fail. Before to implant a prosthesis, a medical device, we can observe that there were problems due to the particle debris and the foreign void reaction and the osteolysis and the failure of the implant. So, before to implant a prosthesis, a medical device in general, it's necessary to evaluate the tribological behavior in which the wear rate is estimated and the load, the surface texture, etc. So, generally, there are two categories of laboratory tests: wear screening device and or quick test. This kind of tests are fast and they provide information exclusively on the intrinsic features of the material studied, without reproducing either the feature or the shape of the implant or the environment with which it will have to interact. The other kind of tests are the concerned about the simulator. Simulator is a machine used to reproduce a joint articulation under conditions approximately those occurring in the human body. Our simulator has 12 stations, and they are filled with bovine calf serum and activated with some necrotical products, and it runs for million and billion cycles. In this result, we can observe some results of different polyethylene, ultralight molecular weight polyethylene tested against metal alloy, and with a good result obtained in the comparison with the worldwide result about this composition. Other tests performed with our simulator were on ceramic nanocomposite and with a different percentage of alumina at 100%, 8%, and 75%, with a good wear behavior with regard to the pure alumina. And the recent introduction of an innovative hybrid bearing, ceramic and metallic intertame, claim to reduce the ion release, wear particles, and the breakage of the ceramic insert rim. So these new couplings, ceramic against metal, were tested with our simulator and showing some results, bad results with in comparison with the pure alumina. A brief digression about the knee anatomy. The knee is a complex matter. Leonardo da Vinci developed an atlas with the perfect anatomy of the knee, and the knee can be associated with a mechanical system in which it can move following some degree of freedom. The femoral extension, anterior and posterior movement, internal and external rotation, varovalgus, medial lateral, and posterior displacement. A knee prosthesis is constituted from femoral component, usually in metal alloy, a meniscal bearing usually in polyethylene, ultra-molecular weight polyethylene, and a tibial plate. They are fixed on this is a section of the knee simulator. They are fixed on the simulator, and our simulator has a 4 degrees of freedom: femoral rotation, axial load controlled, and anterior posterior displacement, and internal external rotation. All these prostheses are tested with this knee simulator, following standard guidelines. The ISO standard for the knee wear test 14243 parts 1, 2, and 3, and our simulator work in following the part 3 because it is move in displacement control. I would like to show you some recent results about with the use of the knee simulator, in which we tested new femoral component in the zirconia toughness alumina, coupled with the standard polyethylene. This is a view of the simulator in run, with the knee prosthesis against the polyethylene on all knee simulator, and the results are are blinded because is patented this test, anyway they showed a good comparison with the literature. In the hand, which parameters control the in vivo? Well, the weight, the size, the gender, or the activity. In my opinion, goals of the tribology is to perfectly mimic the in vivo situation, quantify the wear amount, allow the development of safe and efficient products. Particles could be a critical aspect of the biotribology. We have to think that every patient is different. Experience, in my opinion, is the key to have valid results. So, the biotribology of the future. I think that we have to improve the materials. Research about new materials, different prosthetic design, simulation of daily activity, and in silico approach for hip and knee. In particular, in this context, a new sentence in the field of the wear or total knee replacement is presented by not only tests that level walking, not only wear tests in which is tested, is simulated only the level walking, but also perform realistic simulation of motor tasks, like the star ascent, chair sitting, rising, squat, the so-called daily activity. Or, in addition, if we consider that the preclinical wear tests for total knee and hip replacement are carried out by using a mechanical simulator that have a longer duration and they are very expensive, so that a new way, in my opinion, to have a new wear test could be a novel in silico approach for wear calculation in lubricated hip replacement. These first results are promising. Thank you very much for your patience and attention.
Thank you, Saverio. And we can move to the next speaker, that's Luca Cristofolini, that will tell us about measuring strain in hard and soft tissue. We have accumulated a little bit of delay, so please try to keep in the length of originally planned for each intervention. Luca, your turn.
Thank you, Fulvia. You should be seeing my slides. Good morning, everybody. It's nice to see so many people connected. I didn't realize that 30 years had passed until Marco told me about the idea of organizing this meeting. So I also went back through some memories, and that's how it started. This is me with a slightly different haircut a few years ago. One of my first weeks in the lab, you see an empty lab behind me, and I had a happy face because I had just come back from my Erasmus experience in Greece. I was there doing my first training on bioengineering, and I must thank Professor Angelo Cappello, who encouraged me to take this career. At that time, it was quite unusual to believe that a mechanical engineer could become a bioengineer, but Angelo thought that I could do it, and I'm grateful to him for having encouraged me. My other supervisor at that time was Professor Alessandro Freddi. You see him at my graduation, and again, he was quite brave to think that biomechanics could have some space in our mechanical engineering department. At that time, it was not a common thought, but again, he supported me in this career and in growing in the lab. So some of the first things we did was to stick strain gauges to bone to measure deformation, and study that also Marco mentioned earlier focused on the deformation in the femur induced by the muscles. So we devised an experimental setup, and you'll see many of the pictures from the old years are black and white sketches. That was the main way to publish in journals at that time. So in this experiment, I was pulling ropes to simulate the effect of the muscles, and I was using strain gauges to measure the deformation. This is a femur with a few strain gauges, but in most cases we're using uniaxial ones, which were cheaper and easier to acquire. So with this experiment, we were able to measure the effect of the different muscles and how they affected the strain distribution on the surface, so as to design the optimal experiment with all the muscles that actually needed to be incorporated in an in vitro testing. We did a lot of experimental work, but also methodological investigation. In every step, we went through the validation and assessment of the errors, and we tried to reduce or at least put under control the uncertainties. So we focused on how the mispositioning and misalignment of the strain gauges could affect the measured strain. It's very difficult to do experimentally because you need to remove the strain gauge and put it in a different position, and it is hard to control the actual position. So this was actually the first time when we decided to combine experiment and FE modeling. At that time, Brian McNamara was working in the lab, and this was a very cool finite element model at that time with many elements, probably 3,000, and it ran on the very expensive computer that Marco mentioned for a couple of days to be solved. So Brian used this model to simulate a mispositioning of the strain gauges and misalignment, and this way we were able to see which errors and which positions would provide larger or smaller errors, so which places were more or less reliable in measuring strain. We also worried about the effect of measuring the average strain on the grid surface. And again, the strain gradients are not easy to measure experimentally. So we used, again, this simulation to assess the effect of a small and a large strain gauge and how this would underestimate the measured strain. We also wanted to see the effect of using a uniaxial gauge, which was cheaper and easier to use in measuring strain, as opposed to measuring all the components of a strain using a 3-axis strain gauge. And we observed quite large errors. So from then on, we actually used only 3-axis strain gauges. We played with strain gauges also to measure something different. We tried to measure what happens inside. strain gauges, as you probably know, are designed to measure surface strains, but we wanted to see what happens inside the cement mantle surrounding a hip stem. So we had to face the challenge of incorporating strain gauges in a known position and make them deform correctly together with the cement. And we also had to check that this would be reliable, so we designed a number of experiments to measure the errors or the artifacts induced by incorporating a strain gauge inside a material. Sadly, we found out that we had quite some artifacts when the strain gauge was incorporated in the bone cement, so we realized it was a problem. Then we realized it was a big problem, and then we thought this was a great opportunity to, again, combine the experimental measurements, the calibration coefficients, and FE models to provide the information to correct the readout. So we built a loop where the experiments were validating the FE model, and the FE model was improving the experimental measurements. This translated to a set of experiments also in collaboration with Victor Wade, who was our host at that time for a couple of years as part of a large European project. And we mapped how this on the bone surface, but also in the bone cements, were modified by the simulation of a fibrous tissue layer, and in these graphs also by simulation of bone remodeling. Again, this was part of a loop where the FE models were validated, and at that time we were collaborating with Nijmegen, the group of Ruud Huiskes. So we published a paper where the bone strains and the cement strains were measured and simulated under different simulations of bone adaptation and fibrous tissue formation. We use this technique also in other devices later on. This is a resurfacing prosthesis with a minimally invasive design. And again, we wanted to measure the strain in the bone cement. So this technique could be applied later on in several instances. This is how we were measuring strain on femur. So back on the bone, we're applying 16 strain gauges, typically on a femur, 3-axial strain gauges. So it's a total of 48 grids. We simulate physiological loading conditions and also sideways fall. This allowed us to do some basic science investigation. These plots show the alignment of the principal strain when we tilted the femur at different angles. So we found that the femur is optimized to have the principal directions always the very narrow angle with respect to the femur. So this allows the principal strains to be aligned with the main directions of strength of the tissue, and it is very robust to different loading directions. And this is not the case when you happen to hit on a side and have completely different loading. Again, this was also part of the interaction with the FE models. This is the work that we were doing with Enrico Schilea and Fulvia Taddei, a very extensive validation that allowed Enrico to identify the best parameters for modeling the elastic properties and to predict fracture of bone under different conditions. This is the tibia being loaded under different loading conditions. We applied 28 strain gauges, 28 3-axial strain gauges on each tibia. So this study involved a total of more than 500 strain gauges. I think this is the world record in terms of the number of strain gauges. In this experiment, we were investigating, this was an idea of Mateusz Juszczyk, one of my PhD students. We investigated how the loading condition affects the stress distribution, and by combining this with the morphological analysis, we tested the hypothesis that the tibia would be optimized for some loading conditions and not for others. Here you see that for torsion and axial loading, there are large strain gradients all along the tibia, so different strain values. And conversely, when a cantilever load is applied, the stress and the strain are amazingly uniform. Now, this loading condition corresponds to the anteroposterior force that you deliver to the tibia during walking. So this confirmed the hypothesis that this is a uniform stress structure optimized to have minimal amount of material with a constant safety factor all along the bone. We did similar work also in the vertebra, placing as many strain gauges we could put around the vertebral body. That was 8. simulated different loading conditions, axial loading, bending, torsion, and so on. And again, here we observed the structural optimization that led the vertebra to have a quite uniform distribution of strain around the vertebra with a certain loading condition and quite non-uniform for other loading scenarios. We applied this method also to investigate the effect of cement augmentation. This is a project we did together with the group of Stephen Ferguson in Zurich. This is a system for delivering a control of cement in the vertebra, and these are the strain modified in the vertebra from the natural condition to the augmented condition. And essentially, we found that if augmentation is not properly performed, you have a worsening rather than an improvement of the loading condition inside the bone. Again, this was part of also a validation study, so also here we had an intensive interaction with the FE modeling. Now, the fun part of our work is also to break bones. This is the cathartic part of our experiment. So this is a broken femur. When you see a broken femur, you don't know where fracture started. You just see how it is broken. So we started using high-speed videos to acquire the fracture event and to observe how fracture starts and propagates with high-speed cameras, which could acquire images between 10 and 20,000 frames per second. This was very nice. We were the first to do this on the femur. It's also very expensive. One day, again, Mateusz came to my office, said, why don't we just paint very tiny lines on the femur with a conductive paint, which you can carry shop and connect them to a CPU so that you can sample them at few megahertz, and when the line breaks, you monitor a fracture. And yeah, I said, good idea, why don't we try? And this is the result. So yeah, here you see that fracture starts at certain points, but this is just one line cracking, then nothing happens for a few hundreds of milliseconds. So the femur is taking up energy before catastrophic fracture occurs quite some time later. So this way, in a way, Mateusz was able to observe how fracture starts and propagates in the femur in a way that could not be seen just from this sort of video. We were not totally happy with strain gauges because strain gauges are measuring strain only where they are applied. So we started with a full field technique parallel with strain gauge. Essentially, this is a plastic material whose optical properties are affected by strain, and when it is bonded on the material with a reflective adhesive, a polarized light is crossing the material and reflected back. So by measuring this effect, you can observe fringes that show the magnitude and direction of principal strains. So this is how a hip stem was affecting the strain distribution in the proximal part of the femur, and it's a full field image. And also you see how it's distributed on the resection surface. So where strains are larger, how they are aligned, and so on. It looks nice, but it has a lot of limitations. It requires a lot of time to prepare, a lot of manual skills. It's time consuming, and it has limited precision due to the methodology and to the reinforcement effect. So we were very happy when a new technique came, correlation, which requires a contrast pattern, black and white on the surface, cameras acquiring a calibrated vision so that you can monitor subsets of pixels and see how they move, and by deriving you can compute the strain distribution. It can be very precise or very bad depending on how you use it. If you do careful optimization of the hardware and software parameters to obtain the minimum error, you can achieve a positioning error, an error in the measured position of the order of 1 micron on specimen of the size of one large bone, and strains can be measured with a precision of around 100 microstrain, where the main source of error is typically noise. So we were measuring the effect of the presence of a hip cap and how loosening under cyclic loading is affecting the strain distribution in a stable and in an unstable implant. And we were also able to measure the displacement. You see that the cap here is quite tilted. So a surgeon, Francesco Traina, asked us also to investigate different surgical techniques inserting the cap shallower or deeper in terms of stability. So here we were able to measure the permanent migrations in 3 components and rotations, and to provide an indication which technique is providing smaller motions, which is, of course, the target. In the collaboration of the company, we were testing also 2 techniques for revision surgery with a standardized bone graft and with an innovative resorbable material. And we were measuring, again, how permanent migrations and inducible motions grew throughout the site test to show if this material was suitable or not. We are doing also a lot of work on the spine because DIC is very good at measuring what happens in soft tissue. This is a project in collaboration with Aki and Wilke in Ulm, where we were testing cadaveric spines, and we're using our low-cost version of the DIC and their spine tester. Here you see the deformation in the anterior spine ligaments in terms of stretch, tensile and compressive strain. You can see the individual fibers of the ligament. You see the effect of the bulging of the underlying disc. We could even observe the effect of the osteophytes in terms of local peaks of deformation here and there. This is the new system that we are using, which has 4 cameras and allows to observe the specimen all around, almost all around. It also incorporates a system for tracking fiducial markers, and this makes it much easier to interact between FE models and experiments. This is an ongoing research with Marco Palanca, where we are investigating metastasis on around 40 specimens. So this is how the deformation is changing in the healthy and affected vertebra when the load is applied. And thanks to the DIC system, we are able to watch what happens all around. Now the video, for some reason, stuck, but okay. Essentially, you can see what happens all around the specimen. It's a shame that the video does not run properly. Okay, so we were able to see what happens all around the specimen. We also work on primary tumors. This is a project with the group of Alessandro Gasbarini and Giovanni Barbanti at Rizzoli, where we are investigating the effect of primary tumors on the strains in the vertebra. These are 3 specimens with 3 different primary tumors, and this is how the strains are concentrated in some spots around the tumor. To come to a conclusion, where we are trying to go next, well, we are, as you can guess, we are trying to combine DIC and FE modeling to exploit the advantages of experiments which have the anatomy and material properties of a real specimen. FE models allow to explore more scenarios and estimate what we cannot measure experimentally. The real challenges are how to fuse and register the data, how to translate boundary conditions, and to make the 2 systems really comparable in quantitative terms. Another exciting challenge is to combine surface analysis with a volume correlation so as to combine the optimal measurement on the surface from the IC and the accurate measurements from DVC, which can only work properly on the inside of the structure. And again, the main challenges are registering the 2 systems. Well, these are the acknowledgements. I'm sure I forgot some names. These are the people that I worked with in these 30 years. I've been very lucky to meet so many different people who provided very different input and suggestions for the different projects. So I would like to acknowledge all my past and current co-workers, and thanks everybody for your attention.
Thank you, Luca. So it's time to the last presentation of this session. It's Cecilia Persson. She will talk about the bone factory from cementing to 3D printing. And I cannot see her. Is Cecilia present?
Yes, I'm here.
Oh, great.
Hello.
Hi.
Hi. Trying to share my desktop. My name is Cecilia Persson. I'm a professor at Uppsala University in Sweden. and I would like to talk a bit about bone today and how to replace that. And since it's a bit of a journey through times we're talking about today, I would like to start with my first cementing business in Bologna, and then skipping a bit and going to what I work on today, which is mostly additive manufacturing or 3D printing of materials and implants for bone. So to me, it kind of started in Bologna, and how did I end up there exactly? I did a European materials degree, so I started in Sweden, went to France and Spain, and during my last year project in Spain, I went for a 2-week exchange to Naples, and I asked them where should I go if I want to do a master thesis in biomaterials or biomechanics, and they said Rizzoli. So there I went for my master thesis, and you let me in, even though I sent you this picture of me on the CV. But of course, I got rid of the dreads before I arrived in Italy. I then went on to do a PhD in Leeds, and when I finished in 2009, I went back to Sweden, and I've been at Uppsala University since then. So bone cements, we've already heard a bit about bone cements today. Of course, you can use these to fix joint implants, and that is what we did, and those types of cements that we looked at. And Marco mentioned briefly as well that one of the things we did was to look at the effect of the addition of different antibiotics to the bone cements, and see what happened to them then, because this is something that several surgeons did in the operating theater. You added commonly used antibiotics directly to the cement, and it wasn't really known what effect this had on the mechanical properties. And we showed in a few studies that some of the antibiotics, vancomycin for example, could have a significantly negative effect on important mechanical properties of the bone cements. After my PhD thesis, I actually continued to work with PMMA-based bone cements, but now in a different application, so in the spine. And here, of course, the cements were taken from the application in the joints and used instead in the spine. In a minimally invasive procedure, we inject the cement, it hardens in place and stabilizes osteoporotic fractures. And this is a very efficient pain relief method, but what we saw was that in many cases, you got an increased amount of additional fractures next to the treated vertebrae. And one of the reasons for this was believed to be the high stiffness of the bone cement. So in also one of the projects that Marco mentioned before, the VPHOP, which was led by Rizzoli, from the Swedish side, we looked at adapting these bone cements to the weak osteoporotic bone, so that we could avoid unnecessary additional fractures. And we managed to find an additive that worked quite well. And we continued to work with this and showed in human ex vivo studies that it was possible to restore then the stiffness of osteopenic human vertebrae rather than increasing it. And this is actually was also the start of a company that I founded together with another researcher, and we are going into clinical trials next year, actually. So that was kind of the foundation for me, but what about non-permanent implants? So these are examples of course, implants that you want to remain in the body, but if you have, if you want a temporary fixation of a bone fracture, for example, what would be nice is if you had a degradable material, so something that gives temporary support until you get the regrowth of the body's own tissue. You don't need a second surgery then to remove the implant, and you then also have, of course, a decreased infection risk since you don't have bacteria that attaches to the implant. And this is, of course, also highly relevant today with the increasing antimicrobial resistance where we risk having millions of deaths every year. And in some cases, there are solutions that work quite well. So, for example, here you can see after a tumor resection, you can fill the void with resorbable cement that is replaced by the body's own bone over time. This is an okay solution, we believe. However, when you have larger defects like this one, if you can see my pointer here, it's a lot more difficult. So what you may have to do then in order to get bone regrowth is actually to make a new small fracture that can heal by the body itself. And then you move this piece of bone towards the other one very slowly over time, so about 0.5 millimeter per day. And this can, of course, then take some time between 6 and 12 months, unless you get an infection, and it, of course, takes a lot longer. So even though it's, of course, fantastic that you can actually have bone regrow in this way, from a degradable material perspective, it's not really solved. Then here comes also a new manufacturing technique. So 3D printing, for example, gives new possibilities. One could imagine that you could print something that is patient-specific, that you get then an improved fit of the implant, and in some cases you also want the improved aesthetics. So in the case of maxillofacial applications, of course, this is extremely important. What you can also do is create very complex structures. So you can get something that has a high porosity but still has quite good mechanical properties. You can also design pores in the shape and size that you want to be able to actually get a good biological response. So in this case then, what you would like to have is something that perfectly fits this defect and degrades over time and is replaced by the body's own bone, and you don't have to have this very big structure that also increases the risk for infection and so on. But what material can you use? The available degradable polymers and ceramics today are too weak. So what we thought was, why don't we go for a metal then? There are not that many degradable metals that the body can accept, but one of these are magnesium-based alloys. So can we 3D print this? These types of alloys already exist in implants. This is an example of a screw. But it's not evident to just print the material. Not all materials are printable. And there's also a lack of knowledge on the effect of manufacturing technique on the resulting microstructure and thereby macro properties. One of the most promising methods for printing magnesium alloys is powder bed fusion using a laser beam. So you see an example of magnesium powder to the left here, and you've probably seen this, but what you do is you melt one layer of powder at a time so that you get the object that you desire. When it comes to magnesium, we have certain challenges. Magnesium is a very reactive material, so it forms an oxide directly on the surface. Also, it has a very small difference between its melting point and its boiling point. So the trick here is to get the high enough energy to be able to melt the material, break the oxide, but low enough so that you don't get too high evaporation of magnesium and you get a depletion of the main element in the alloy. So what we have done is try to print then a magnesium alloy that is commercially available in these types of screws that I showed before. And what we've seen is, of course, if you have too low energy, you get a lot of unmelted material and pores. If you have too high, you get an excessive evaporation of magnesium and cracks in the material. And you need to find this optimum energy input to be able to get a non-porous material. If you look at a cross-section of these materials, they look very different to the regular microstructure. You can see the melt pools here, and also you get different types of precipitates, different phases in the material. And this can, of course, have big effects on corrosion properties and mechanical properties of the material. But what we've at least so far shown that it's possible to print relatively complex implants. So these are just example spinal fusion spacers, and also the bulk material is higher than 99.9% density. And what we're going into now is, of course, looking more into detail of the process parameters and the powder composition. Can we make this better? How does this affect the microstructure and thereby the corrosion and mechanical properties of the material? So just a brief summary. Of course, these bone cements are still being used. They're very good for different types of permanent applications. But with 3D printing, we see a lot of new possibilities in terms of maybe being able to heal larger defects in a better way. Recently, we got a 10 million euro grant to start up a competence center within additive manufacturing for the life sciences. And there are also some possibilities for both an assistant professor and some PhD positions coming up. That what I wanted to mention. Finally, I just wanted to say thank you to the Rizzoli Institute for having me. This was in 2005. It was a great time. And of course, I'm also very happy to meet all the friends at different conferences around the world. That was it for me. Thank you.
Thank you very much, Cecilia. And sorry again for the technical problems. So we join back in plenary at 11:40. Okay. Thank you, everyone.
Thank you to all.